know there was some concerns that the first assignment had a lot of questions, I think like 10 questions, and that's not going to be the norm, right? So I just introduced the first assignment that way so that you can go back and really recap different concepts you already know. So made it a bit long, but from the next assignments, the load will be a lot lighter. So again, if there are more concerns, come to us and we'll be happy to address them. But any other questions? Both logistics or even some of the background I covered last week before we proceed. So I hope you could make it to the recitation yesterday, or you have a background in convex optimization, right? So is that a fair assumption for everybody? So what we'll do today is look at optimization first, right? Like independent of machine learning, what are the core optimization questions and how do we tackle it? And then at the end, I'll just think about how that relates to machine learning problems, right? But this lecture will be mostly only about optimization. In the later ones, we'll connect it back to learning and what are the branches. So what's the main challenge? Like you looked at convex optimization, and there we have so many things that can be very well described, right? So if you have a convex function, there is only one globally optimal solution, and then you have these local methods that will also reach the global optimum, right? Because there's only one global optimum doing like gradient descent, or the second order methods was Newton method. These are local methods. They're only making local improvements, but they lead to a global guarantee. On the other hand, if you have non-convex function, right, this is not going to be true, right? So if you make local updates, you cannot expect to go to the globally optimal solution, right? For instance, if you're descending here, you will go to the global one, but on the other hand, if you're descending here, you'll go to this local minimum. In fact, you may not even get to a local minimum, right? So there are all these questions we want to address, and when I say non-convex optimization, that can mean everything that's non-convex, right? So that's too big a set. I mean, there are all kinds of NP hardness in that set, so we are not going to keep it that general, but maybe we'll make some further assumptions on that. On the other hand, we're also going to ask for something weaker. If I can't get to the globally optimal solution, can I be happy with just the local solution? Is that good enough for me? Right? Maybe in some applications it is. And even what does it take to get to a locally optimal solution? Right? Even that's non-trivial for general non-convex problems. So that'll be the strategy here. We still want to keep simple methods. Our methods will be still local search like methods which will build on gradient descent and Newton's method. On the other hand, we won't guarantee global optimality, but something much more local. And that's still a better guarantee than having nothing, right? And in many applications that could be good. So that's the starting point, right? So, but before we get to that, what do we mean by these weaker guarantees, right? So if we don't just go with global optimality, what are these weaker notions? So what kind of optimality conditions can we have? So what's the most basic condition or the starting condition for an optimal point? Right, I mean, like if you...
Feasibility?
So right now, let's even do just unconstrained. So this whole lecture will be just unconstrained optimization, right? So in R to the D, so we'll just not impose constraints. That's going to make it a lot harder in some of the questions we'll ask. I think I have an optional reading for constraint optimization, what it takes. But in this lecture, we'll limit to unconstrained. So for unconstrained optimization, what is the starting condition? Like if you expect a solution to be optimal, what condition should it satisfy?
The first order derivative vanish?
Yeah, so it's the first order derivative, right? So I'm going to use this notation. Usually if it's a vector, like I want to use the gradient, so I'm going to use this notation. Right, so x is a vector in many of the cases. So this should be 0, right? So is this enough for a non-convex problem? So what's a counterexample of where the gradient can vanish, but it's not the optimal solution?
Saddle point.
Okay, we'll get to the saddle. I mean, the first obvious one is here, right? So that is local. So the second one is, yes, so it could be even not even a local minimum, but a saddle point, right? So we'll call these points where the gradients vanish as stationary or critical. Right, so this set of points that satisfy this will be called, this is the convention, right? We call them stationary. And there's a reason why it's called stationary, because we'll see that, gradient descent, Newton, they'll all be stationary there, right? You won't move if you're at this point where the gradient vanishes. But then what's the next condition? Like if this is not enough, what's the second order condition we want? For minimality, let's say just for minimization. Right, so we look at the second order derivative. So what's the condition we need of this? Yeah, so it should be like positive definite, right? So, I mean, if you want it to be a strict local minimum of the second order, you need it to be strictly positive definite. And that's intuitive to see. I mean, of course, in one dimension, if the second derivative is positive, that means it's kind of slowing down and you will get to a minimum point. Right, so that's the intuition. And now with the vector case, this is a matrix, and you now have positive definiteness instead of just positive. Right, so this is intuitive, right? Because if you're like having a minimum, right, the gradient kind of should slow down, right? Because ultimately it should go to 0, right? The change in the gradient should slow down.
Positive side.
So that's what I mean. If I want it to be strict, then we'll need it to be
For example,
definite.
the function x4 has a 0 threshold at 0.
Yeah, so those are called degenerate points. So, I mean, a strict one won't have degeneration. That's just a, right, it's still a local minimum, but something that's called a strict is called non-degenerate, but that is convention. Yeah, but that's a detail. Right, so with these two, what can we get? With these, what we can get is, a local minimum, right? So it can be a local minimum, but there is some basin around which it will get at, there'll be, where this is the minimum. So there's a basin of attraction. So if you did like gradient descent in this basin, you can get to that local minimum point. Right, so in some cases, so now it was talking about when it is only positive semi-definite. So if you have like some 0 eigenvalue, right? So if there is some lambda is 0, so there is some 0 eigenvalue, then we call it a degenerate point. And in that case, you actually need higher order conditions to test if it is a local minimum or not. So I'll come to that as well in a second. Magic. I don't know what created that, but I'll come to that case. Right, so in this case, it's already straightforward. You don't need any higher order derivatives. But if the Hessian is degenerate, you will need to go higher. Right, so what's the other viewpoint of seeing this? I mean, you can see it like diagramming, like, through a figure that having this second order condition will ensure it's a minimum. But the other tool, I mean, almost the mainstay in any of the optimization ones is what? Taylor series, right? So it's really the Taylor series that will be used a lot. And it will be like bounding the various order derivatives that will help us come up with guarantees on various algorithms. So the way to see these conditions in the Taylor series is, so if you recall Taylor series, you're going to expand around a point x. And since this is vector, I will have like, products. Right, so, and then the second order term is now the Hessian, sorry. Right, and so on. So now you can see that if the gradient is 0, you really have to check the second order term, right? That's the only way you can determine whether the function in the local neighborhood is increasing or decreasing. And if the Hessian is positive definite, if it's strictly positive definite, then you know everywhere else in the neighborhood, the function is strictly larger. Right? So this point has to be the minimum. Is that clear? So that's how you determine, it's through Taylor series that, that it's a strict local minimum there. But if you have degeneracy, what you do is you actually go to the next order term. So there'll be like so this is where we'll need a tensor notation, but I will not give that in detail here, but something like if it's a third order derivative of a vector, it'll be a tensor. So we'll cover tensors in a later class, so I don't want you to be too much worried about it, but think of it as, in one dimension you would have a third order derivative, right? And now if it's a vector, you will need to come up with a way to express the Taylor series even in the third order. So without worrying about what this means, the main thing to remember is, you don't just look at the second order derivative, you have to look at higher order derivatives if you find degeneracy here. Because you cannot determine whether it's strictly increasing or decreasing only looking at the second order terms. But that's an additional kind of complication you will see in some cases. But these are the basics, right? So the basic notion is you always start with the first order derivative. If the first order derivative is non-zero, I mean that's not a stationary point, that's not a critical point. But if it is 0, then you have to check the second order conditions, right? And through the second order, you determine if it's a locally minimum point. And if it's strictly positive definite, it is. Right, so that's our starting point. And now the question is, what if this is not a strictly positive definite matrix? So what are they called then? That's our saddle points. Right, so that's like when you have stationarity, but the second order condition is not true, then you have a saddle point. So Watson is possibly the simplest example of a saddle point. Yeah.
X squared plus y squared.
So, right, so if you have like, I guess, two, so in this case, if you have like x equals y, or in this, or 0 or 0, right, that's so you're minimizing. Although in the unconstrained case, this is actually going to be like, I guess, I mean, in this case, wait, is this what you mean?
We can do it how we want.
No, but if x is and y are 0, right? I mean, yeah, so if it's, the minimum in this case would be like negative infinity, right? So yeah, so for the constrained one, you know, you could make it interesting, but for the unconstrained, this is, so can we look at another example? So this won't be, I mean, we always want to assume a lower bound, otherwise it's not well behaved. Can we think of another example of a saddle point? Even just in one dimension before we go to the dimension.
Actually, we can add the y to the fourth power to the original example.
So x squared minus y to the fourth?
No, x squared minus y squared plus y to the fourth.
Oh, okay. So I could write it as y squared into 1 minus y squared, right?
Yeah.
Okay, so in this case, what would be the minimum?
No, 0 is the point, and this lower bound is this is unconstrained in the same problem.
Hmm?
0, I think 0 and square root over 2.
So, do you want to come and write? That's easier.
So, the Hessian matrix and
I mean, you're doing the scalar case, right? Or
yeah, the two images.
Yeah.
So, this I think 1 minus 2. And still y. That is. So this one is 7 point.
So 0, 0 is a saddle point because there's one negative eigenvalue. Do the others see that? So before this, can we do a simpler one? There is a simpler, I mean, what's the simplest one? We'll come to this in a second. But I mean, with just one variable, in just one dimension, what's an example of a saddle point? X cubed, right? So that's what I was expecting. We'll come to this. Let me finish x cubed and then.
X cubed is not lower bounded.
Huh? Yeah, so it's not lower bounded, sure, it has the same issue. But then I mean, the saddle point is easy to, so from this you can't see why it's a saddle, right, because it's just all degenerate. So in one dimension, you cannot have a non-degenerate saddle point, it will only be degenerate. By that I mean the second derivative will be 0, right, so you would not have, you can't have a non-zero second derivative and still be a saddle point in one dimension. But in 2 dimension, it's possible, and this is 1. So before that, let me show that kind of visualization of the saddle point, right? So why do we call it a saddle point? So if you visualize a horse saddle, what you have is, in one direction it's increasing, and in the other it's decreasing, right? So if you're going like this, it's like, increasing, and then the other direction it's decreasing, right? So it's both a direction of increase and there is a direction of decrease. Right, and that's why it's called a saddle. Yeah.
But if the Hessian is just positive semi-definite,
it's not, right? That's the idea. Like when this condition is violated, so when you have both positive and negative eigenvalues.
yes, but I mean, if that's a definition of saddle point, then chances.
No, this is not the condition.
Oh,
this is when this is violated. This is the condition for optimality.
I see.
So when there is a local minimum, you want it to be, when it's a strict local minimum, you want it to be positive definite, and if it's non-strict, then it could be positive semi-definite. So a saddle point is one where you would have both negative and positive eigenvalues. Right? So a local max would be the opposite, right? In the local max, you would have negative definiteness. And so saddle point is where you have both, right? So it means in some directions the function is increasing, in the other directions the function is decreasing. Is that clear? So that's the main, and again you can see this intuition from the Taylor series. I mean, forget about the third order, we're just looking up to second order. You can see here that, if you like choose directions along the positive eigenvalues, this would be, if it's a stationary point, the gradient term is 0. And the second term, if you choose the positive eigendirections, the function will be increasing in those directions. And then if you choose the negative eigendirections, the function will be decreasing. So you have both increase and decrease that's happening at the saddle point. Right? So in one dimension, it's not so interesting because it's degenerate. Right? In higher dimensions, you get this interesting phenomenon. Right? So that's the basic distinction, and that's important, these the classes of stationary points. Okay, any questions here? So now, in this, again, I guess you can work out the Hessian and you can check that if there's both positive and negative eigenvalues, then you would have saddle point. Any questions here? So everybody's with me? Good. So far this is great. So so what's kind of the additional detail is if you have degeneracy, you really have to look into higher order terms and it can get more complicated. So the papers that also deal with this, but I won't go into details, but there's some interesting visualizations of those kind of higher order functions. Right? So think of like this is the wine bottle. So if you have the wine bottle, you have like this, like a circle, and then everything is kind of peaking. Right? So that's like now there is this whole circle. That's the minimum, right? But then there is there is degeneracy. So these are more complicated. You can have this inverted wine bottle where you have that peaking. This function is known as a monkey saddle, so there is like an equation which is in the paper that will say what it is. But just, I don't want you to worry too much right in the beginning on this, but I'm just pointing out that it need not even be this nice kind of a saddle shape, right? You can get a lot more complicated shapes if this becomes degenerate and you have to check the higher order conditions. So that's kind of the point I'm making with these figures. So there can be, the idea is it can get very complicated, right? Like it's sometimes even just the second order condition is not enough and you have to keep checking the higher order conditions. And you can get extremely complicated optimization landscapes, and that's why this is so difficult. I mean, we're training all these big deep neural networks and they can have arbitrarily complicated optimization landscapes. But this is more as kind of showing that the pictures can get very complicated, the landscapes can get very complicated. So when do saddle points arise, right? So I just want to kind of here relate it to the machine learning problems of why do we care about saddle? So one is because we are doing a lot of non-convex optimization now. We are no longer forcing our loss functions to be convex. If you stack these many layers of a neural network, it becomes non-convex. Right? So why is that non-convex? You can, there is a very simple way to see that to me is through symmetries. So if you have like now, so I'll introduce the details of a neural network in later lectures, but I think a simple network everybody understands, right? So you have some network, you have like a layer with some non-linearity applied, let's say ReLU or some non-linearity, right? So you have like a weight matrix, you have a bias, and then you keep like repeating this again and again. Okay. And so now the problem is there can be like many symmetries here, right? So you can have like cases where you can like, if this is a ReLU, you can like switch the scale. Like you can multiply a value here and then divide by the same value here and it's the same output answer, right? You can permute the labels of these middle neurons here and you will still get the same answer, right? So there are all these symmetries, and if there are symmetries, it cannot be a convex problem, right? Because with symmetries, what we have is not just one unique globally optimal solution, there will be multiple global optima, right? Because they're all giving you the same value. And so that cannot be a convex function unless everywhere it's flat, right? That's the only possibility. And why is that? So just to kind of make that point much more precise, let's say there is a function of, let's say, m dimensions and its permutation symmetric, right? So that means if I permute the indices, it's still the same value. So I'm assuming a permutation symmetric optimization. So now in this case, let's say this is the globally optimal solution. If you permute it, it's again a globally optimal solution, right? And so that means if you have now some convex combination of these two solutions, let's say even just the average. So I'm taking like the midpoint of these two solutions. So if it is a convex function, this should be having the same value as well. Do you see that? Because if it's a convex function, what this says is the function should lie below the line joining it, right? That's the definition of a convex function. But then we are saying these two are globally optimal, so the only way is everything is globally optimal along the line. So it's inherently these are non-convex once you have symmetries in your system, right? And when they're hidden layers, by default there are symmetries. And same with latent variable estimation problem. Later lectures will introduce probabilistic models and we'll say there are some variables that are hidden, we cannot observe them. And that will introduce the same symmetries because you can permute the labels of those variables and you will get the same answer. And that's why it's very critical to think about saddle points, because once you have symmetries, right, you will have multiple basins. Like each one is a different basin of attraction. And the only way is, like, if the two are joined, it has to go through saddle points, right, because there has to be the transition. And so in this 2D, you can like visualize here, there's one basin of attraction, there's another one, and that has to move through saddle points to go from one to the other. And in fact, as you increase the dimensionality of your problem, as you increase the number of coordinates here, the number of saddle points can be exponential, right? Because the symmetries, first of all, can generate exponential copies, right? And then that can also really explode the number of critical points. And that's why this is so hard, right? So we not only have, you can't possibly kind of search through all of them, you have to be happy with the local solution. And the hope is that local solution is good enough because there are many good solutions, right? There's lots of symmetries, so maybe you're not missing a lot by looking at the local solution.
Ask one quick question. Does the symmetry mean that if I can find the local minimum point, it is as good as the other minimum point?
It's not guaranteed, right? What I mean is maybe it's hopefully okay. There's no guarantee because you could end up generating another local min that's bad. But the hope is there are so many good local solutions that are good because of all the symmetries that hopefully you're getting to the right one.
So by good, are you saying that they are identical in terms of their...
Yeah, because of the symmetries. Yeah, but there's no guarantees. Right? So that's the intuition, yeah.
Can you provide some examples in machine learning application that use symmetric notation?
Here, right? So you can permute the labels of these neurons and you will get the same answer. Because that's an intermediate layer. Like whether you call this neuron 1, neuron 2, right, doesn't matter. You can switch them and the answer will be the same. Right? Or the scale symmetry, if this is a ReLU, which is a rectified linear unit, you can multiply with, say, make this twice and then divide in the layer above, it's still the same answer, right? Because you can switch the scales.
But with respect to the original input data, it's not symmetric.
No, but it's the middle one, right? It'll be symmetric with respect to what the, the intermediate layers you can switch, right? So going from here to here, essentially you switch here and then you switch also here, right? So. And the simplest one, think of Gaussian mixture, right? So you have now two mixture components. You just call this mixture 1, mixture 2, or mixture 2, mixture 1. It's the same. Yeah.
The fact that you get saddles, is it useful for identifying that maybe you have insufficient training data, or that maybe the model is insufficiently complex to model the training?
What's your intuition of how saddle can help with that?
Well, if like say if you train a bunch like a set of neurons and looked at they all behave a certain way, but you then cluster them for behavior to kind of diverge.
Oh, so you mean like with small amount of data it's training, and then with more data it actually gets worse? Is that? Sorry, can you make that?
Like say if you just have one layer and you're training on like a Zor, maybe like the layer you don't have enough layers to model that, and so you maybe get like two groups of like optimal solutions based on that model. That's saddle, right?
Two groups? What are these?
Like it would either cut this way, like if you have a Zor, then it would either cut this way, they're both valid optimal solutions. That's a saddle. Like that's the what you end up training to. Right?
Okay.
Is this like fact useful for like realizing that you don't have enough complexity in your model?
That's so I know I need to understand that more closely, but I think what you're saying, my interpretation is, if you don't have enough data or enough capacity in your model, not data, right? So we're not talking about data, enough capacity, you're saying we could get stuck in a saddle point.
Yeah.
So if there isn't enough capacity, that has to even say something about the global optimum, right? So it need not even be a saddle point. The global optimum itself is bad. Like, you're getting a bad training error and you need to increase. So it need not be saddle, right? So it's not connected with whether it's saddle or not. I mean, what the saddle will kind of tell you to do is, you can do much better, right? The saddle is not even locally a minimum solution. It can be really bad. So you don't want to get stuck there.
So are there intelligent ways in the context of neural networks to design to build asymmetry to not create these problems for yourself?
I mean, once you have hidden layers, right, anything that's kind of hidden, by definition, that would be having symmetries, right? And in fact, you want to incorporate symmetries. I mean, there's even the argument that we should add more symmetries because, we want to incorporate invariances in our model, right? So from modeling perspective, that's not going to happen. So we have to think from the optimization perspective, how do we handle it?
If your hidden layers aren't fully connected, wouldn't that break the symmetries?
When they are...
Because you're saying that all of the intermediate neurons are connected to all of the bottom layer and the layer above.
Yeah,
If you break
yeah.
the symmetry and remove links, will that break the symmetries up?
Yes, because then you're constrained, right? You can't freely switch them. But then, you're assuming, you have to then design what the sparsity pattern is and if this is good enough, right? So I agree, that's one potential way. But sparsity people have, first of all, most of the common ones are the convolutional layers, and then it gets more complicated, right, with the convolutions, what does sparsity mean? So it's not clear, I agree, that's one way to break it, but it's not clear what impact that will have on the final answer. But that's a good point, yeah. Any other thoughts? Right, so that's the one setting. Because of symmetries, we can expect a lot of saddle points, exponential numbers, right? Then there's the other interesting phenomenon that happens, especially with these modern neural networks, right? The way we are training it is making it highly over-parameterized. So in the later lectures, we'll really go into what a capacity of a neural network means. But for now, think of it as you have a lot more parameters than what your data set is, right? So you're making this very big, you're introducing these networks to have a lot of capacity. And so that means with, in these networks, you could perfectly fit to your data and have zero training loss. Right, so think of this simple example, don't worry about the general case. So in this simple example, you have these two clusters, right, and you want to separate them. This is perfectly separable, right? So you have the red cluster and the blue cluster. There's a line where you can get perfect separation. So in this binary classification problem, you can perfectly say, you know, which one is in cluster red and which one is in cluster blue, right? So in a single line, or this what we call perceptron, I hope many of you have heard of perceptron, right? So otherwise, you know, go again, refresh that. So what that does is essentially gives you the sign of, what it does is take the sign of W transpose X plus the bias, right? So you just take this. So this is a perceptron model. And in this case, you can just have, you know, one line that perfectly separates it. So these are called linearly separable networks. So instead, but we won't train a perceptron. Instead, what we'll do is we'll introduce two neurons here, right? And you could just have the sine function or any others too, but let's say you have just the sine non-linearity here. So if you're like now making it a combination of two perceptrons, this is over the capacity, right? You don't need two perceptrons. Just one perceptron is enough to perfectly separate the data, but you're making it bigger. So in this case, there are results that show, in fact, your set of critical points will explode, right? So what it says is, in a smaller network, if there was a critical point, that will become a set of critical points in the bigger one. So you're kind of having this multiplicative effect where a single critical point can span a whole big set of critical points in the big one. And that's again the symmetries, right? Because you can kind of like exchange like kind of how much capacity you put in one neuron and the other very easily. Because there's a lot of flexibility here. Yeah.
And just to make sure I understand, when you say the smaller network, what you mean is sort of a path in the bigger graph, for example, the right hand.
Yeah. I mean, the smaller network is, let's assume there was a network that generated the data, right? In this example, it was just a perceptron, like that's enough for me to separate the data. I mean, more than generate, I mean, what can separate the data from the smaller one. So that's called realizable, right? So you can realize that model in the smaller network. But instead you decide, I'll just put a bigger network and train that. And so that's introducing these complexities, right? So that's something to keep in mind, because people always want to train big networks because, you know, there's some benefits to doing that. I mean, one benefit is if the global optimal solution now becomes a big set of globally optimal solutions, the hope is it's easier to reach them. Right? So again, it's an open question whether this makes the problem harder or easier. Right? So there is evidence of both these directions, so I'm not going to take a stand whether it makes it harder or easier. But you can see it definitely increases the set of critical points when you go to a bigger network. Right? So it will also increase the number of points, I mean the set of points where there will be globally optimal or nearly globally optimal solutions. But it will also explode the number of saddle points.
Is there a quantitative relationship between number of layers and the number of
No. I think it's, for small ones, people have tried to do it through algebraic geometry, but nothing, you know, like kind of even asymptotically, unless you make some very strong assumptions and invest. I would say it's an open problem. Okay, so I'm giving you these examples as kind of intuitions to see why the landscape especially in neural networks, is so complicated. Right? It's very hard to analyze them. So we can't hope to kind of directly do it, but we can hope if the algorithms can escape saddle points effectively, that's hopefully good for us, and we can train the networks better. Any thoughts? So what we covered so far is mainly to understand that there were, just to recap, right, like that there is local min, local max, this is, if you're doing minimization, we want to at least get to the local min, and we want to be able to escape saddle points. Right? And I showed you examples of why the saddle points are going to be a lot in machine learning problems. Yeah.
Is it not the case that stochastic gradient always escapes saddle point?
I'll come to that. That'll be the next part of the talk. There are exact rates and exact guarantees for that.
Because you always escape saddle point.
With high probability. I mean, once it's stochastic, there is.
Even if you're not stochastic,
I'll come to
you
that.
have to get very unlucky
Yeah.
to be able to manifold to a saddle point. Even if you're not stochastic.
I'm coming to exactly that question. So I'm coming just 2 minutes to come to that. But anything else before we get to that question? Okay, so now we'll come to that question of what, how can we escape saddle points, right? So the first we'll do is just deterministic methods. So we'll come to stochastic after that. But if it's completely just deterministic, like gradient descent or Newton's, what do you think will happen at a saddle point? What happens if you run gradient descent at a saddle point? Right, so, if you want to recall gradient descent, what that was doing was taking a descent step along the gradient, right? So what happens if, if there is a saddle point here? If you're near a saddle point, what happens to gradient descent? Slows down, right? And in fact, at the saddle point, it won't move. And if there is noise, that's a different story, and I'll come to that. So whenever a gradient descent by itself encounters a saddle point, it'll just stay there, right? It won't, and this is bad. So what about Newton's method? So let's again recall the Newton's method, right? So what does the Newton's method do? So essentially, taking the inverse of the Hessian, right, and multiplying with the gradient. Do people remember why this is the right thing to do in the convex case? I think this was covered yesterday, right? A very quick one-line answer.
Second order approximation.
Yeah, so it's second order approximation, right? So you're essentially like, optimizing it, just assuming the approximation of the function up to second order and optimizing that. And that's nothing but a quadratic function, and so the optimal solution will be. So what happens to Newton's method near a saddle point? It's the same thing, right? So again, it slows down and it will just stay there. So both gradient descent and Newton's method will treat the saddle point the same way as it does second order or a locally optimal point. Right. So by themselves they're not enough, and now the question is, what can you do as a deterministic method? What can you do to escape saddle points? So what would be an intuitive way to overcome this without adding noise? We'll come to that. That's a whole other class of methods, and that's where we'll focus a lot more attention once we finish this.
Would you artificially increase the learning, the n?
The eta?
Yeah.
But if I'm already at a saddle point, right?
It's like
Doesn't.
it's like going up.
But it's still like, right think of it as if you're right on the saddle point, you can't do anything, right? And the thing is, if you want to guarantee everywhere, and you could say like, oh, what's the chance of hitting the saddle point? But if we have these kind of surfaces, there are a lot of saddle points, in fact, saddle surfaces, right? So it's like you can't hope to always even avoid it. Yeah.
By having each update be on like a subset of data, then in theory, like the exact location of saddle point will move around slightly.
So that's noise, right? You're made randomizing. So I'll come to, so I'm saying without introducing noise. So if it was purely deterministic method, which for machine learning is not so relevant, but I want to introduce the concept as an intuition before we get on. So we'll come to those. I mean, that's kind of like what, you know, what noise does to escape will be very interesting. But let's leave that aside for a second.
Using information like the eigenvector corresponding to the largest negative eigenvalue of the Hessian.
Exactly, right? So if you are at a saddle point, right, like what should you do in terms of the Hessian directions? So let's say this is a saddle point, and I can compute its eigen decomposition. Let's say V1 through Vk are the eigenvectors, and then lambda 1 through lambda k are the eigenvalues. And let's say I've ordered it, right? So the lambda 1 is the highest, and then it's decreasing. So at some point you would have like the zero crossing, right? So there's some positive eigenvalues, and then there's some negative eigenvalues. So what should you? So suppose you know this, I can check the Hessian at a saddle point, and I can compute its eigenvectors and eigenvalues. How can I use that information to move away from a saddle point?
Move along with the linear combination of the eigenvectors that have negative eigenvalues.
Right. I mean, you can pick any of these directions, right? So if you move in this subspace, you're always guaranteed to move away, right? Because those are directions where the function is decreasing. Right? So you can do that. So what's the kind of direct way to kind of tweak this equation to do that? Like, can you just kind of tweak it a bit to kind of do a similar update, but ensure that you're always doing it on a positive definite matrix? Like what would, I mean, this is not positive definite, right? But how can you make this positive definite?
Regularize it, like plus a lapse or something.
Regularize, is that what you said?
Yeah.
Yeah, regularize it, yes, exactly. Right, so instead of this, you can add now some quantity times identity. And that would make it, and of course you have to choose it the right way so that it becomes positive. So that's the basic intuition. I mean, if you can do regularized Newton's method, then that's a fix. Like that'll escape the saddle point. But the main challenge is like kind of, you want to like decide how to figure out what this gamma is, what this regularization is in each step. And for that, you have to first compute the eigenvectors. You have to decide all this is a mess, right? So, I mean, intuitively, this is what you should be doing, but doing it explicitly may not be, in practice, such a great thing. So what I'll introduce now is actually a very, to me at least, it's not intuitive, right? Like in the sense of like, there's a method which will ultimately reduce to something like this, but takes a very different route. I mean, in retrospect, it's kind of obvious why it ends up reducing to regularized Newton. But for that, we'll kind of go back to Taylor's expansion, and we will do an optimization based on that. So first of all, we'll make some more assumptions, right? So I think somebody was asking me about guarantees earlier, right? So what's the guarantee that you will actually go to at least a locally optimal solution, and can you go fast? right? Because I think yesterday, for convex optimization, you may have seen rates for gradient descent, Newton step, and all that, right? Like how fast does the function go? And we can do the same in the non-convex case for local optimum, and that method is called cubic regularization. You know, the techniques in this paper I think are really awesome. Like there's many different threads coming together. I'll not cover all of them, but at least I hope to give you the intuitions which I think are really key. So what's the first one? First one is we're going to make first, so if you want to make, like, I mean, at the core of it all is going to be Taylor series. Right? So if you're doing Taylor series, so the very first step, what should you do? You want to think of making just a first order approximation. Right, so. And now if you want to upper bound this, of course this is not going to be exact. Right? So when I wrote this, I mean, for general functions, this is not true. Instead, I want to bound, like I want to say, when will this be an upper bound? Right? And for this, that means I have to bound the second order term, right? Like all these residual terms, I have to come up with a bound. And so, you know, so if I say that, let's say alpha 2. So how should this L depend on the Hessian? If I claim this is an upper bound, because what does the Taylor expansion say? The Taylor expansion says that there's a Hessian term and a higher order term. Right? So if you assume here that this is the maximum eigenvalue, right, on the Hessian everywhere, then you can come up with this bound. Okay. And it's also called gradient Lipschitz because it's nothing but giving you the Lipschitz constant of the gradients in. Right, so this is for first order approximation. If you want to do as a bound, I mean not an approximation, a bound, right? Like you're using only the gradient information and you're coming up with an upper bound of the function. Right? And I think from this it's kind of clear if you only optimize this upper bound, that will be gradient descent. Right, because you're going to take the gradient step. Right, because you pretend this is your function, like the optimal thing to do will be the negative. And in fact, from that you can even see the step size will be like 1 over n. I mean, that's a small exercise, I'll let you do that. Right, that's nothing but just differentiating it. Do you see that? So if you pretend that this is your actual function and you want to optimize for this delta x, right? That's the gradient descent. Do you see that? Yeah? Yes? No? Take the derivative, right? So f of x is equal to, L times delta x. Okay, so if you are doing just upper bound on the gradient, so this is an additional assumption, right? So this is now an assumption. It's not going to be every arbitrary function. You're making an assumption that there is a Lipschitz bound on the gradients, or equivalently upper bound on the eigenvalue of the Hessian everywhere. Right? So we're making assumptions, and then hopefully that way we can get guarantees. So what the cubic regularization says is, why stop at the first step? Let's do an approximation or an upper bound for the next step. So you can take the same trick and take one more term. Right? So So I'll still keep the second order term because I want to go to higher order. So what should like a higher order term be? I mean, there's already the, I have the name of the algorithm, so. Like what would make this an upper bound, right? And then I need an additional assumption, right? So first of all, what should be the assumption? I mean, so far I assume a Lipschitz bound on the gradient. If I want to bound the next order term, what should you assume? It's okay, take a guess.
The cubic of delta x.
Right, so, okay, so there's a cubic term, I think that's kind of something you can see, right? And let me just also put 1 over 3 because that's likely. But so now I put some constant m, and how is that m related, right? Like what assumption do I need in terms of that? Like, I mean, how do I extend this kind of assumption to the next order, this Lipschitz assumption? Yeah, so you have Lipschitz Hessian, right? So you assume now it'll be the, here it was the L2 norm, right? I mean, typically L2 you could also do other norms to L2. Here it will be the spectral norm. That's again the typical one, you could do other norms, but we won't get into that. Right, so So this is now another assumption. So we're making these assumptions, and for many problems this is quite okay, right? So like kind of, I mean what this effectively is saying is the third order derivative should be bounded, right? So here it was saying the second order derivatives are bounded. And sure, there are problems that don't satisfy, but many well-behaved ones will be satisfied. And so what the cubic regularization paper argues is that this should be the natural extension of gradient descent. Right? So for the first order, we did an upper bound. So instead of optimizing the original function, we are optimizing the upper bound. And for minimization, that's okay, right? Because you're hoping if you're optimizing an upper bound, you're still making like descent and you're making progress. And so you hope that you will do the same, but this is a better, sharper approximation, right? So you hope the second order bound is tighter compared to the first order bound.
Is there any sort of intuition or some sort of qualitative information you can use when you look at a problem to determine whether or not these sorts of Lipschitz constraints are well motivated? Or
So think of it as I think. So when would the Hessian not have, even for first order, right? So this is almost like a smoothness condition, like if you, it's called smoothness condition in fact, and yes, there are some, especially with ReLUs that's not smooth, that's going to be an issue in neural network context. But again, you could maybe smoothen it and this would be a higher order version. In fact, this would be even harder to violate compared to this, right? Because you're saying the third order, especially if this is satisfied. You have this in the Hessian, but somehow the third order is wacky and unbounded, then that's kind of, I don't know, that's hard to imagine.
Can you explain why you did the spectral norm instead of the L2 norm?
Because it's matrix, right? So this is a Hessian is a matrix. You could also, everything you can work with other norms if you want. Just the convergence rates, everything would be expressed in these other norms. But the standard is 2 norms. Any questions? Yeah, so so the two different, in a board there, I was talking about regularized Newton's method, and here I'm talking about this cubic regularization, right? So I'm arguing that we're optimizing the upper bound involving the second order terms and the cubic regularization. And what Nestrov's paper shows is the two are exactly the same. Underneath doing this cubic regularization, you're effectively doing like a regularized Newton's method. And in fact, it's automatically picking what's the good regularization at every point. I think that's beautiful, right? So somehow, at least at the outset, you really can't see why the two should be related. But it's kind of like automatically deciding what kind of regularization to pick. And you can kind of see that here, right? Because it's saying, don't just do this Hessian, but also you need this regularization, right? So it is regularizing the Hessian and kind of doing a regularized Newton. Any questions here? So,
a factorial on this readers?
oh, yeah. This, the 6, right? Sorry. Here, thanks. Forgot my Taylor series for the 6. I think I did the 3 even the first time. It's erased now. Any other questions, thoughts here? So, I encourage you to read the paper because I think there are some great tools. So far what I mentioned was just do this minimization. Right? Looking at this is not convex, right? So this is a problem. But then, what Nestrov and Polyev show is there's actually hidden convexity. You can actually solve this problem to optimality in each step. So there are so many details like that I won't cover, but I wanted to just give you the intuition that, by thinking about upper bounds on your function and optimizing that, you can find effective ways to make progress and actually give guarantees on how well you can do. So this one I want to move on unless there are further questions. Yeah, so let's go to the next topic. So this is all beautiful, but for machine learning, we don't do deterministic methods, right? So we won't be getting the exact gradient or even exact Hessian, right? Because if you think of a machine learning problem, what you're going to have is a subset of your data, right? And that's called the mini batch. And so if you're computing the gradient on a mini batch, so it's averaging those data samples, that's inherently a random quantity, right? It's not going to be the expectation, there will be the gradient in expectation, which is the true gradient. So there's going to be noise, and so we want to be gradient descent, and so that's called stochastic gradient descent. Right? So there's stochasticity in your gradient estimation. Right, and that's because you're randomly sampling your data and only computing this gradient over those samples, so that's a random variable. That's not going to be your true gradient. And so now with stochastic gradient descent, what can we hope, right? What can we expect will happen? So let me come to that. So this was... Yeah, so first of all, stochastic gradient descent is the most standard method, right? Almost all papers in deep learning will be mostly using SGD, and if it doesn't work, then there are some variants that kind of follow, additional parameters to overcome that, right? But the most common is SGD. And so now the question is, what can we guarantee for SGD, right? So, can we we were talking about saddle points earlier, and we were asking, can gradient descent escape, and we said no, gradient descent cannot, right? But what about now stochastic gradient descent? So what can noise do, right? Any thoughts? So if you're doing stochastic gradient descent and you're on a saddle point, let's say you're even on a saddle point, what can you expect to happen?
Resemble the batch of points.
So, I mean, there is a patch of points, so that's the underlying mechanism, right? So somehow you're getting a noisy version of your gradient. So let me like say this is now, I mean, I have to introduce randomness, so maybe let me call this tilde. Like tilde is your noisy version. So the true gradient in expectation will be the true gradient, but this only noisy version. So if you're near a saddle point and you do SGD, what will happen?
The expectation is zero, but it's a random variable, so you're not guaranteed that it's zero.
So if there's enough like variance, then hope it'll escape, right? Because there is, or it will escape. So with again, it's going to be with some probability, right? It's not going to be with probability 1 because this is now a random process. But if you have noise, right, even though the true gradient is 0, there's going to be randomness, and if there's enough variance, you will escape this, right? So it's intuitive that it will escape. So noise is actually a good thing, right? So now we are training all these neural networks. I showed you that there can be just so many enormous number of saddle points, right? But this noise could be really helping us escape them, and it is helping us escape them and overcome all these saddle points. So noise is a good thing, but the main, I guess, technical question is how fast will it escape, right? Because if it takes, like in the worst case, an exponential amount of time as you increase the dimension, right, that's still bad, right? So the main challenge in the papers that I'll show now was to ask how quickly can I escape saddle points under stochasticity. So let me go to that. Yeah, so the main kind of challenge there, so I think I have the figure, let me show. Yeah, so this is the figure from a paper that, I have that in the references that shows how to escape, what's kind of the landscape to escape these saddle points. Right, so before we see this, so let's kind of first think about this problem again. So here we were saying, if this is a saddle point, we'll have some set of positive eigenvalues and some set of negative eigenvalues. Right, so now the question is there going to be enough directions with which you can escape very quickly? And we said with the second order method, it's kind of if you directly compute this and choose these directions, for sure you'll escape. But the main challenge now is just with the randomness, is that enough to escape? So what this paper in Aranga is one of the authors and also my collaborators, what they did was to say like you will do stochastic gradient descent, but they also assume like an explicit additional noise. Because who knows, like you can't really control the noise in terms of how much stochasticity is in the gradient, but what they showed was if you ensure that there is enough added noise, then you can show that it will escape. So they said that let's add some uniform noise and some ball of radius r. So of course how you pick r is a detail that's in the paper. But the main idea is you should make sure there is enough noise. Right? Otherwise, you may not escape. Because we know gradient descent will get stuck, so you don't want that to happen. So you add sufficient amount of noise to your stochastic gradient descent, and then we can ask, can this escape? And what like all this analysis turns out is in terms of like, so you have this kind of uniformly random vector in this ball. Right? So this vector can be in any of these directions. And so now you want to ask, in this ball, which, what is the size of the space where you can escape and what's the size of the space where you get stuck? Right, so essentially there is some part of this subspace that will be the positive eigenvalues, and that's where you get stuck, right? Because if you're moving along positive directions, there's no improvement, right? You want to move along the negative directions. So you really want to hit these negative directions, and the main question is, what is the probability this random vector will be in this escape region, right? That's the main question you want to ask. And what they showed was, essentially this region where you get stuck, like these green bands here, and this is in dimension 2, this is in dimension 3, will be a lower order manifold. Like it'll be just a small band. It won't occupy a big part of the space, right? The volume of this band will be small. And so that means the probability your random vector will be in this band is small. So with high probability you're escaping, right? So, and that's the main kind of concentration analysis you need in the random case to argue that you will escape fast enough.
So this argument shows that stochasticity is useful for escaping saddle points. One thing I've often wondered is, putting aside the saddle point issue for the moment, if you're not at the saddle point, you're just going downhill, does stochasticity hurt you? Because intuitively the gradient direction is the best direction most of the time, apart from saddle points.
So if it comes to machine learning, it's not clear, right? Because, I mean, the big elephant in the room, we all know, will be generalization. So I'll come to that in the last slide. We're trying really hard to optimize, but is that even the right thing? So you kind of, jump to that. But we'll address that, and that's but that's open, right? So I think, at least for me personally, and for many other researchers, there is much more evidence that noise is helping us than hurting us. There's robustness and there's regularization. There's so many things that noise gives us. And that's why I think it's also the reason why so many of the classical optimization algorithms, which have amazing guarantees, haven't had a big impact in machine learning, right? Because you don't just want to optimize. But I'll come to that in the end. I mean, that's what I was hoping would be like the ending point. But yeah, so this paper I've also listed in the references. I think it has some beautiful concentration analysis to argue why having this random vector you can hope to escape saddle points well, right? And the main intuition is there's only going to be a small region where you're going to be stuck. Like most part of the space, you will be making progress and you will be escaping it. So that's why, don't have to worry about a second order method. Just adding noise is enough, right? And that's so much more efficient than going to second order. Any questions here? I know I didn't cover any of the details, but I hope the intuition is okay. Yeah? And then the next part I want to briefly cover is on, scaling up optimization, right? So we won't be doing a lot of systems in this course, but it's in the real world we have to run this and we have to scale up our computations, right? And at some point you cannot put all your data in one processor. Whether it's one GPU or CPU, it's not going to be enough. You want to distribute it. If you have lots of data, you have big models, you can't do all the optimization in a single processor. And in this case, if this could be multiple GPUs or any processors, right? You have to transmit, you have to exchange what the local computations were. So let's say you're just doing stochastic gradient descent, and in this case, each local machine will have its estimate of the stochastic gradients. But then it has to exchange with all the others and average it, and that's how come up with a global estimate of the stochastic gradient, right? So then you can all the machines can make the updates and then they can keep proceeding. And in the simplest data parallelism, what happens is different machines are given different data, right? So they just have their own data, they compute local gradients, they all exchange that, compute the global gradient, and they come up with an answer. So in a recent work with me, Jeremy, and Jaha were the first authors, and Kamya, where is he? He was here. And then he disappeared, and he showed me. So what we asked was, do you really need this full gradient information? Right? I mean, it's going to be expensive to communicate because, now once we're doing the distributed setting, it's going to come with an actual cost, right? You have to communicate, and if you have to have a large number of parameters like in a neural network, this is not going to come cheap. And so we asked, can you just compress it? Like, don't send the full gradients, just do a compression. And the simplest form of compression was just take the sign. So in each coordinate, just take the sign and ignore every other information. Right? And in the central processor, you will be just taking the majority row. Like, what does machine 1 say? What does machine 2 say? Machine 3 and so on. What's the majority saying? And I'll declare that's the true sign and transmit it back. And so what the update here is, instead of doing the gradients, I'm just updating with the sign of the gradients, right? So let's just even do the single machine. Let's just even do the single machine update. Although the motivation is really in the multi-machine, right? So in the single machine, what you're now doing is just taking the sign. And the question is this enough, right? Like, do you need the full gradient, or can you expect even with the sign, it's going to be enough? This seems really drastic, right? You're throwing away all the information about what the values are and just looking at the sign. So what we show is, surprisingly, actually, you can prove that this will converge to a first order point. You could also extend it to second order analysis, but in the paper, we started with the first order. And so what we're saying is, this is enough if you want to get your gradients to be small. You don't even need the full gradients, the full precision gradients. So, that was comparison, but this is the main result, right? So, these are, you can derive the rates of like the stochastic gradient descent, how fast does it converge. And this analysis is actually not, really that much more than what I said here. So you make this approximation or this more an upper bound on your function, and you argue like in each time step how much is this bound changing, right? Like how it is improving. And you kind of like aggregate all that and you can come up with a rate. So that's for the stochastic gradient descent, and for the sign as well, you can show that there is a rate but with a different geometry. So instead of like a rate on L2, you're getting L1. So there's a different geometry, but it still converges.
Does this approach require a level of conditioning on your data such that the gradient magnitudes would all look the same?
So it'll assume like this kind of smoothness, right? So it's gonna, assume like smoothness in the function, but when it comes to stochasticity, that's the noise, right? So this is the bound or the noise. So there's a variance bound of noise. So you just need to assume the noise is bounded. And how that noise is generated through the data, that's a complex thing, right? That's an additional lower level of detail.
Do the units need to be normalized between components in the vectors?
So, here we're just taking the sign, right? So every coordinate has the same unit.
So if the data, everything has very different units, but in your gradients and all of your steps are with the same unit, that seems like it would cause issues.
That's what, it will still converge. It's going to say the rates are different, how you measure it is different. But if you only care about convergence, it's going to converge. So which one will be a better rate will depend on those properties.
How much like the step size data?
So eta is usually in the SGD case, eta is selected as 1 over L. And that's kind of showing up again if you do this, right? Because here if you optimize this, like you want this to be 1 over L.
So is it fixed step size?
Huh?
Is it a fixed step size or?
This is what the theory says in practice people, do all kinds of things. I mean, what this is saying is for this step size, you can come up with a rate, right? So at least in the simplest analysis, that's what it assumes. But they're also more and more looking at things.
So these results have this assumption that.
So in this one, I think what we did was a large batch analysis. Like we assumed that the batch size is large.
And the step size is huge.
But or equivalently, you can switch the two, right? At least for STD, you can switch the two, not for sign. But the main kind of point I want to convey here, since we're out of time, is that you don't, sometimes you think you need a lot of information to do optimization. That's not necessarily true. Right? So noise helps, and you don't need full precision gradients, so stochastic gradients. Just this. So I can't cover more, unfortunately. So let's leave this here. But because I really want to kind of end the lecture by really, debating what's the role of optimization in machine learning. Right? So I want you to go with these passing thoughts that, if optimization may not be enough, you also really want to think about regularization and generalization. And we'll discuss that in coming lectures. Thank you.